All right, let's go. Number 6, lava worlds, where the ground is the ocean. Some planets never cool down. Lava worlds are a class of rocky exoplanet orbiting so close to their host star that their entire day-side surface is a global magma ocean, with rock vaporized into a mineral atmosphere that condenses and rains out on the night side as silicate droplets. 55 Cancri E, orbiting its star in only 17.7 hours at a distance of roughly 2.4 million kilometers, was one of the first suspected lava worlds. Observations by the Spitzer Space Telescope revealed a dayside temperature of approximately 2,700 degrees Celsius and a nightside temperature of roughly 1,400 degrees Celsius. A day-to-night temperature difference so large it is inconsistent with a bare rock surface and suggests either an active silicate atmosphere or large-scale lava flows transporting heat around the planet. James Webb Space Telescope observations published in 2023 detected thermal emission from 55 Cancri E showing brightness temperature variations consistent with a thin, dynamic volatile atmosphere, possibly produced by volcanic outgassing, being recycled continuously by the extreme temperature gradient. The tidal locking of these planets means one face bakes perpetually under a star at distances less than the distance from Earth to the Moon. The rock does not have a chance to solidify. The surface is not stable enough to have geography in any recognizable sense. Mineral clouds form above the magma, raining out silicate particles that fall back into the glowing surface below. A lava world is not a dead planet. It is geologically maximally active, a world in constant, catastrophic geological flux, where the ocean is made of molten rock and the weather system is composed of vaporized minerals falling as molten rain. Number 5. Rogue planets, entire worlds frozen in the dark. Billions of planets are drifting through the galaxy with no star. Rogue planets, also called free-floating planets or interstellar planets, are planetary mass objects ejected from their birth systems through gravitational interactions with other planets, binary companions, or passing stars. Population estimates based on gravitational microlensing surveys suggest that these objects are extremely numerous, potentially outnumbering stars in the galaxy by a factor of several. The Milky Way may contain trillions of free-floating planets, ranging from sub-Earth masses to super-Jupiters, all moving through the galactic disk in the dark, heated by no star, bathed in no light, cold to temperatures approaching the cosmic microwave background temperature of 2.7 Kelvin. On their surfaces, any atmosphere or ocean would be frozen solid. Any volatile ever present on them has long since either escaped or become permafrost. But the interior of a rogue planet with sufficient mass retains heat from its formation and from the decay of radioactive elements for billions of years. For sufficiently massive rogue planets, the combination of a thick hydrogen atmosphere acting as an insulating blanket and internal radiogenic heating could sustain liquid water oceans beneath the ice shell, entirely without any stellar input. We have found microlensing events consistent with populations of rogue objects down to Earth mass and below. One rogue planet candidate, CF-BDSIR 21490403, is a free-floating object in the AB Doradus moving group approximately 130 light-years away, estimated to be between 4 and 7 Jupiter masses, young enough to still be warm from formation. The galaxy is full of worlds that nobody is looking at, traveling through permanent night, and some of them may not be entirely cold. Number 4. Ocean worlds with no shore, no sky, no land. Some planets are water, not planets with water. Planets that are water. Theoretical models of planetary interior structure predict that planets forming in the outer regions of protoplanetary disks can accrete enormous quantities of volatile ice, resulting in ocean worlds tens to hundreds of kilometers deep. Global oceans with no continental crust, no exposed rock at the surface, and liquid water extending to depths where pressure is so extreme that exotic phases of water, hot ice phases like Ice 6 and Ice 7, form solid layers at the base of the ocean despite temperatures of hundreds of degrees Celsius. The pressure overrides the temperature, producing solid phases of water that are denser than the ocean above them. The ocean floor of a massive ocean world is therefore a layer of exotic, high-pressure ice, not rock, and the geochemistry of the ocean has no input from rock weathering in the way Earth's ocean chemistry is maintained by the dissolution of silicate minerals. For life as we understand it, the rock-water interface is critical. It provides mineral nutrients, pH buffering, redox chemistry gradients, and the geothermal energy sources that support chemolithotrophic metabolism. A planet-sized ocean with no rock-water interface is chemically impoverished in ways that may preclude complex biochemistry indefinitely. Kepler-22b, Kepler-62f, and multiple candidates from the TESS mission are consistent with ocean world interior structures. We cannot yet confirm ocean depths from transit photometry alone, but the models are robust, and the frequency of these objects in the galaxy may be very high. Entire worlds of nothing but ocean, thousands of kilometers deep, with no shore, no sediment, and possibly no chemistry complex enough to begin. Number 3. Hot Jupiters are being stripped alive. The largest planets in the most extreme environments are actively losing their mass. Hot Jupiters, gas giant planets orbiting within 0.1 AU of their host stars, receive radiation doses thousands of times greater than Jupiter receives from the Sun. The upper atmospheres of these planets are being photoionized and heated to temperatures exceeding 10,000 Kelvin, and the gas is escaping the planet's gravity in a process called atmospheric escape or photoevaporation, forming comet-like tails of gas and metal atoms trailing behind the planet in its orbit. HD 189733b, one of the best characterized hot Jupiters, is losing hydrogen and oxygen at a rate of approximately 100 to 600 million kilograms per second. At this rate, significant atmospheric erosion occurs over billion-year timescales. The extreme ultraviolet and X-ray flux from the host star is the driver, and younger, more active stars produce more powerful erosion. Hot Jupiters around very active young stars may lose entire layers of atmosphere across their lifetimes, leaving behind a denser, stripped remnant. The population of ultra-short-period super-Earths observed by Kepler, dense rocky planets orbiting in under a day, may be the evaporated remnant cores of hot Jupiters that were stripped down to their solid interiors by billions of years of photoevaporation. WASP-69b, observed in 2023, was found to have a tail of helium extending over 560,000 kilometers behind it, more than one planetary diameter of gas being actively blown off per unit time. These are planets dissolving in real time, visible from Earth, being consumed by the very stars that gave them their energy.
Number 2. Pulsar planets. Worlds bombarded by cosmic radiation. The most hostile planetary surfaces in the observable universe orbit dead stars. Pulsar planets are rocky bodies orbiting millisecond pulsars, neutron stars spinning hundreds of times per second and emitting powerful beams of X-ray and gamma-ray radiation, high-energy particle winds, and intense magnetic fields. The first confirmed exoplanets ever discovered before the era of Kepler and hot Jupiter detections were the 3 planets found orbiting pulsar PSR 1257+12 by Alexander Wolszczan and Dale Frail in 1992. These planets orbit a neutron star remnant of a supernova, receiving a radiation environment unimaginable by Earth standards. At the orbital distance of the inner planet, the X-ray flux from the pulsar is roughly 100,000 times the total solar flux received by Earth. Any atmosphere would be stripped on short timescales by the pulsar wind, a flux of charged particles moving at a significant fraction of the speed of light. The surface temperature is set not by radiation heating, which would cook it, but by the complex interplay of irradiation, atmospheric stripping, and whatever internal heating persists from the supernova formation event. What the surface looks like is unknown and possibly unmodelable with current physics. The rocks, if any remain, are continuously bombarded by high-energy particles that ionize and fragment molecular structures. No carbon chemistry could persist on the surface. No liquid water could exist with the atmospheric pressure stripped away. These planets are not dead in the way a cold asteroid is dead. They are dead in the way an object being continuously irradiated at industrial radiation doses for billions of years is dead. Which is to say, chemically, physically, and in every sense that matters for complexity, beyond recovery. Number 1. Black hole planets, worlds in the dark at the edge of everything. Theoretical physics permits planets orbiting stellar mass black holes, and some may exist. A planet orbiting a stellar mass black hole would receive no starlight. Its only energy sources would be the Hawking radiation from the black hole itself, which for a stellar mass object is at a temperature of tens of nanokelvin and negligible for heating, and whatever accretion disk emission the black hole produces if it is actively feeding on surrounding material. An accreting stellar mass black hole can produce X-ray luminosities comparable to a star, with a spectrum peaking in the X-ray rather than visible light, and a planet in the right orbital position around an X-ray binary could in principle receive enough energy to warm its surface to temperatures relevant for chemistry. The geometry would be extreme. Tidal forces at orbital distances close enough for meaningful heating would be severe, and the radiation environment from the accretion disk would include hard X-rays, gamma rays, and a relativistic particle wind. Further out, where tidal stresses are manageable, the energy flux drops rapidly, and the planet would be cold. What makes black hole planets conceptually extraordinary is the time dilation. A planet in a close orbit around a stellar mass black hole experiences time more slowly than the distant universe due to gravitational time dilation. An orbit at a few Schwarzschild radii from the event horizon places a planetary surface in a time regime where 1 year on the planet corresponds to significantly more than 1 year far away. The universe ages faster than the planet does. In the far future, when all other stars have burned out and the galaxy is dark, a black hole that has not yet evaporated remains, and any orbiting body remains with it, experiencing time at its own rate, slowly, in the dark, while the rest of the universe moves toward entropy at full speed.